Okay, today's lesson is on independence, and for the most part, I would tell you, y'all know this, okay? I have talked to you about in this whole section of probability. There are some formulas, not very many of them, and if you have all the information for the formula except for one item, you can always find that one item. So remember what we have talked about before, basically from our previous lesson, and that is an and statement. The probability of A and B is equal to the probability of A times the probability of B given A. Okay? Similarly, the probability of B and A is the probability of B times the probability of A given B. Okay? And I also told y'all in that first one, we talked about peas and carrots, that the probability of B and A is the same as the probability of A and B. Now, why am I saying all this? Because here is a formula, y'all. And if you know two parts of this formula, then you know the third, which is what we have down here. Okay? This is the and statement. This is what they call the conditional statement. The conditional probability of an event occurring given that another event occurred. So if an and statement is what you get when you multiply two events, then a conditional statement is what you get when you divide two events because you're doing the opposite thing. One of the ways I remember the formula is whatever is this second one is always what's my new denominator. Okay, so we're going to talk about some card problems. You need to be familiar with them. And for those of y'all who do not play cards or are not familiar with them, I'm going to give you a short lesson. And that is, first of all, every deck of cards has 4 suits. Probably should have said what those suits are. They are clubs. See if I can draw this. This is going to be kind of funny. Well, let's go with hearts, clubs. There's a club. Spade. That's a really bad looking spade. And diamonds. Okay. So 4 suits. 2 of them are black and 2 are red. So hearts and diamonds. Okay. I'll put them like this. I probably should have drawn them that way. Hearts and diamonds are red, and clubs and spades are black. Okay. And the other thing you need to know that there are 13 cards in each suit. And I guess I should tell you what those are in case you don't know. But you have an ace, and then you have 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you have a jack, queen, and king. Okay, so jack, queen, and king are what we call those face cards. Okay, ace is not considered a face card. Any card that has a face on it is a face card. So you have 13 cards in each suit. 4 suits in a deck means the total number of cards that I have in each deck is 52. Okay, so consider drawing a card from a standard playing deck. Let R represent drawing a red card and the event Q represent drawing a queen. So the probability of drawing a red card, how many cards in a deck? 52. How many of them are red? Well, half of that 52, which is 26 out of 52. What? Oh, poo. I know what happened. I did that wrong. Let's see if I can try that again. All right, let's just put that. So 26 out of 52, and that equals 1/2. Okay. The probability of a queen and a red. Okay, y'all. The key to doing these problems is you need to think about how many events are happening. So when I draw, this is just drawing one card. So how many cards are queen and red? Well, that's the queen of hearts and the queen of diamonds. So that is 2 out of 52, which becomes 1 out of 26. So the probability of a queen given it's red means that I'm going to take my and put it on top of my probability of a red card. And when you simplify that, you get 1 out of 13. Okay, But it's all about I multiply the numbers to get the and I'm going to divide the numbers to get that conditional probability. Okay, so one other important part of conditional probability is determining whether two events are independent. Okay, this is going to be on your test, so you need to make sure and understand this notation. Okay, y'all. If the probability of A given B is equal to the probability of A, or the probability of B given A is the probability of B, then the events A and B are independent. So when you look at these two things, in essence, they're independent if this little part of it doesn't matter. Okay, so let's go look at an example. Consider the event of rolling I'll leave that right there. Consider the event of rolling a 3 on a 6-sided die, the event of getting heads, and the event of getting heads when flipping a coin. So I went ahead and put the sample space here. Makes it a little bit easier for you. So what's the probability of getting a 3? Okay, so when you roll a die and get heads, that's one possibility. I could get a 1 and then tails, or I could get a 1 and then heads. So this is my whole sample space. How many items do I have in there? 12. How many of them have a 3 in them? 2. So the probability of getting a 3 is 2 out of 12, or 1 out of 6. What's the probability of getting heads? Well, how many events have a head in them? How many outcomes, I should say. Each of these is an outcome. How many outcomes have heads? That's 6 out of 12, which is 1/2. So what is the probability of 3 and heads? So how many of those outcomes have a 3 and a heads? I highlighted it in green, and that, of course, is 1 out of 12. Okay, so now we're going to go consider the conditional probability of rolling a 3 given the coin is heads. So the sample space, if I'm given the coin is heads, that means I have to have a heads. So my sample space now, I only have 6 outcomes here. Okay, that's this one. But you can look at it using the information. If you want to apply the formula, okay, what's the probability of 3 and heads? Well, that was 1 out of 12. What's the probability of heads? That was 1 out of 2, or 6 out of 12. Sometimes it's easier if you don't reduce it, okay? And so that simplifies to 1 out of 6. But if you look back, okay, our outcomes were limited, and that's why when we did the problems earlier, the denominator always changed when we were reading from a table when we had a given problem, because that's a condition that we're putting on our probability. So there's only 6 outcomes here, and how many of them have a 3 in them? 1. So that's why it's going to be 1 in 6. So more importantly, since the fact that the coin lands heads up does not affect the probability that the roll is a 3, or mathematically speaking, what's the probability of 3 given heads? You can see that that is 1/6, and the probability of a 3 is also 1/6. So we say the two events are independent, okay? Because it doesn't matter. They're the same. So this little part on that question doesn't have any bearing on our problem. Okay? One more short problem, and then we're done. Independence is less obvious when working from a two-way table where the probabilities are based on data in the table. 100 customers at Mr. Salty's pretzel shop in the mall were surveyed and asked about their purchases. So here is the data set up in our frequency table, two-way frequency table. So we're going to go through and answer our questions. What is the probability of buying a pretzel? Okay, well, how many pretzels do I have? Total number of pretzels is 60 out of total items is 100. So that becomes 3 out of 5. The probability of buying a soda. Again, I have 100 items. How many are sodas? 40. So that becomes 2 out of 5. So the probability of buying a pretzel and a soda, okay, remember that's the intersection. So pretzel and soda is 25 out of, again, 100. So that is 1/4. So I'm going to take that information to find what's the probability of a soda given that you bought a pretzel. So the probability of buying the pretzel and soda, 25 out of 100. probability of buying a pretzel is 60 out of 100. And one of the reasons for doing that, y'all, when you write it not simplified, because then you can ignore the 100s and it's 25 over 60, which still reduces to 5 out of 12. Okay, so compare what is the probability of a soda. Well, that was 2 out of 5. What's the probability of a soda given they buy a pretzel? That was 5 out of 12. So since they are not equal, then the events are dependent on each other. Okay, so you, to finish this packet, have a wonderful problem on the Titanic and finding out whether or not social class had any bearing on their chance of survival. And then after that, there's some extra practice problems in review to see how you might get a variation of this concept in other problems. So, short, sweet. Please don't hesitate to email me or set up a Google Meet if you have any questions. Thank you so much, and y'all have a great day.